Thanks for watching again. This week we're going to be focusing on creating our own radio. Now we've done it in the past, it's a bit outdated. I made it a 7-part video tutorial, which is insane. I wanted to do it in a bit longer video explaining the basics of the dual concentric rotary encoder, how we can use a library to make it easier, and how we can drive the TM16376 6-digit 7-segment displays. That wasn't very hard word to pronounce. Believe it or not, I did it in one take. I did not redo this whole bit. You gotta trust me. So we're gonna be using those. You can also use the MFS2020 displays. If I'm correct, that's the right number. If not, please correct me, let me know. But for me, these are just so much easier to program. The other ones aren't hard as well, but it's just personal preference. For me, it's ease of use. These ones do require a bit more pins than the MFS7219. I believe I keep making up some new numbers, but it's up to you, whatever you choose. Just know that the code that I've been using in this video is aimed at the TM1637. And before we get started, I also wanted to show you that we have a very amazing Discord community going on. You're going to keep updated when the latest video is released. Don't forget to hit the subscribe button as well. And tonight at 2000 UTC, we have our first group flight going on from Whiskey Alpha Bravo Tango towards Whiskey Alpha Yankee Yankee in New Guinea. So if you're interested, go check it out. It will be in the link below. And I hope to see you tonight. Well, today we're going to be looking at a radio that consists out of the active frequency, standby frequency, and a dual concentric rotary encoder to change the megahertz, kilohertz, and swap the frequency. For this project we need an Arduino. I went with an Arduino Uno. You can also use a Nano, Mega, Leonardo, Pro Micro, whatever. We also need 2 7-segment displays. I went with the TM1637 6-digit ones because the frequency has 6 digits as well. We need some cables. We need some male-to-male and male-to-female cables. And most importantly, we need a dual concentric rotary encoder. When I look at my local hardware stores, dual concentric rotary encoders can be quite expensive, so I'd suggest to look up something on AliExpress, for example. They're still quite expensive for AliExpress standards, but $7.49 is way cheaper than the $15 or $20 they usually charge for it. Now, if you didn't pick a Leonardo or Pro Micro, so a Uno, Nano, Mega, etc., it's very important to also include a capacitor. They recommend 10 UF. I've also got it working with 4.7 and something higher than that. So just keep that in mind when you source your parts. Now for the dual concentric rotary encoder, in the article you can also find how you're able to find which pin does what as well. But right now I'm just going to go through it quite quickly. It has an inner shaft and outer shaft, so it's actually 2 encoders into one component. It consists out of 8 pins, from which are 3 pins for one encoder, 3 pins for the other, and 2 pins for the switch. The groups of 3 are an A pin, a ground pin, and a B pin, and the same goes for the other side. So just remember that the middle pin is the ground, and it's A and B is going to be the left and the right. For the switch, it doesn't really matter if we use the left or the right one. For the ground, we can just be using it as an input pull-up. Because it's easier to handle, I've soldered them onto a proofing board. So this is just a little perforated piece of plastic where you can solder your components on to make a kind of PCB circuit. Now I've soldered this with my new soldering iron. I'm totally in love with it. It's the Echo FX88BD. Now let's start by wiring our screens to the Arduino board itself. Now for the screens, they have pins, so we're going to be using the male to female wires, and they are clearly marked VCC, ground, diode, and CLK. Now the VCC and ground speak for itself, which is going to be the 5 volts and the ground wire, and we're just going to slide them over it and stick them into our breadboard because we need a shared common ground line. Now you don't have to color code the wires, but I think it will make sure that you don't short anything if you can visually spot which is the ground and which is the 5 volts by just judging it based on color. So all the other wires aren't really that important to color code. Perhaps it's easy to match the diode with the same color on the diode so you know which wire is which. But for the ground and power, I always recommend to go with a designated red and black or brownish. Once all the wires are hooked up, we're going to be starting by wiring the common ground and the common 5V line to our breadboard. Now the red is going to be going into the red line, and the ground or the black one are going to be going to the common ground line, which is represented by the blue line on our breadboard. As a quick reminder, on the breadboard, the common ground and the common power line will run over the entire horizontal row. So even though they have these little dividers in between of 5 pins, they all are connected. Now on our Arduino, we need to connect the ground and the 5V to the same line as well. Make sure that they match so that you connect the 5V to the red one and the ground to the blue one. The CLK and diode pins of our screens will be connected to any pin that you'd like on our Arduino. Just make sure that you don't use the 2 and the 3, and we come back to that later why that's the case. Now, in my case, I've hooked them up to 8 and 9 and 10 and 11. And here we see why color coding can come in quite handy. I instantly see that all these black wires are going to the ground. So that's exactly what we're going to do. We're just going to put them into the common ground line on our breadboard. Now, when I'm going to code this up, I'm going over this in full detail, but the yellow and green wire are the A and B pin of our encoder. And we need to make sure that either the A or the B pin is connected to pin 2 and the other one to pin 4, 5, 6, 7, doesn't matter. But as long as one of the 2 pins is connected to 2 and from the other encoder to 3, we make sure that we use the interrupt pins available on our Uno. Now I come back to this later why it's important, but for now just hook them up in 2 for the inner shaft or outer shaft, then skip a pinhole, insert the A or the same one from the inner shaft or outer shaft, whichever you took, and then skip a hole, and then just fill those holes up with the B pins. Now that leaves us just with the 2 wires for the switches and to switch in the button, and you can put them in any hole you'd like that's marked with a number or an A in front of it. So coding this up is actually quite simple. We're going to be using the Bits and Droids library and connector to connect with the game and send data. And we're going to be using the encoder library to make it really simple and easy to write code for our encoders without having to do too much yourselves. The links to the library and the connector will be in the description down below. So if you don't have those, don't be afraid. You can just go down there and read up on it yourself, download it and install it on the Arduino IDE. Another option would be to go to Sketch. I'm going to start by including them. Include bits and droids flight connector.h. Should have named with a short name. Include encoder.h. Now the code ends. Also written an article about using dual rotary encoders as a kind of back to basics tutorial. I will link to that in the description as well, just as the code itself will also be obtainable through an article in the link. So you can read up on it in your own time if you're feeling that this goes too fast. If you have any questions, don't forget to just ask them in the comments and I'll get back to you as soon as possible. So Bits and Droids Flight Connector, we're going to create a new connector object. It's going to be false. And we're going to be creating a new encoder. Encoder rotary inner. And I'll come back to this in a second. Encoder rotary outer. Now we have 2 encoders, even though it's one component. We have the inner shaft and we have the outer shaft. The inner shaft has an A and B pin, and the outer shaft has an A and B pin as well. So one thing we do need to know is where are those pins connected before we can do anything with them. So const byte, because it's a variable that's smaller than 255, that is going to be constant. It will never change, and it will just save us some space and memory for our Arduino. So we say const byte let's say inner A is 2. Const bytes inner B is 4. Because we used pin A on 2 from the outer shaft, pin A on 3 from the inner shaft, and then 3 for the inner shaft B pin, and 4 for the 2, 3, 5. Oops, 5. So we do the same for the outer A is 3, and const bytes outer B is 4 then. I had a full blank 2, 3, and 5. Yeah, okay, so 2, 3, 4, 5. That is correct. Now, why did we choose pin 2 and 3? And that is because they have interrupt capabilities. In short, it kind of means that in the previous approach, we always used a polling technique that was constantly looping through the loop block. It was polling the current state of each pin, and if it was high, it was low. We would create some logic that if it's high, low, etc., do this, do that, it goes up, it goes down. An interrupt is basically a principle that makes it possible for our board to not run that code, like the entire polling process. The moment something changes, it will trigger an interrupt, and the board will know, okay, something has changed, now I need to execute this code. Now, because this is a bit more complex than the normal code, you could write this yourself, that's no issue, but we're going to be using a library that has everything in there already. Now, why it's important to use the 2 and the 3, I'm going to show you. Well, this is the Arduino website, and on here you can find lots of information about the board and some of its functions and how to code it up, but it also will give you an overview of which pins are interrupt capable on which board. So let's take the Uno, which we have right here. It has an interrupt pin on the 2 and the 3, while the Mega has a lot more. It has a 2, 3, 18, 19, 20, 21. And if you take something like a Teensy or STM32, it even has way more interrupt pins than an Arduino has. The best performance could be gained by using 2 interrupt pins. So 1 encoder, 2 interrupt pins, so 2 and 3. In our case, because we use the Uno, and I basically used the Uno because lots of people use the Uno, is that it has only 2. So the second best option would be to go 1 interrupt pin and 1 normal pin. So in our case, that's why we did it with a gap in between each time, 2 and 4. 2 is the interrupt pin, 4 is the normal pin, 3 is the interrupt pin for the other encoder, and then 5 is the normal pin. So I hope that makes things a little bit clear. It's a really global explanation of interrupts and why they are important. You could also use just normal pins, but the performance would be, it wouldn't be bad. That's the thing. It would still be very usable, but this is just better. So that's just something to keep in mind. If you want the best, use 2. If you want a better performance, use 1 interrupt pin. And if you're like, I'm fine with okay, it's fine, it's good, just go with whatever you like. So let's go back to our code. So we say inner A and inner B. So what we just said is that Rotary inner has a pin A, 2, and a pin B, 4. So pretty straightforward. We do the same for outer A and outer B. Coffee time. Yes. So let's keep rolling. Now we also have our 2 screens. So I've got to include them. I'm using the TM1637 chip, and the chip is basically just a driver for 7-segment displays or LEDs in general. But why I'm using this is because it's dirt easy to program. The Max 8192, 8129, doesn't matter. The other one that's very, very popular is also a good solution. It just takes a bit more code, and this is just, sometimes I like it to be quick and easy. But for this, we need another library, which is going to be TM1637 underscore 6. TM1637 underscore 6D. Now, what does the 6D mean? It's just a special library for 6 digit, because frequency has 6 digits, like 240.850. I want with these screens. It was a no-brainer for me. So here we go. Now the same can be done for these. Let's make it clear. Here we have a block for the Rotary. So here we have the connector. And let's be concise to then behind this one we do the screens. So once again, const bytes dio active is 8. Const bytes CLK active is 9. Because we have a screen connected to 8, 9, and the other screen is connected to 10, 11. It has a diode, and a CLK pin, and we're gonna need this to define to the object where they are located later on. So const byte dio standby, because we want the standby frequency on this screen is 10. Const byte direct CLK standby is 11. Now these names can be anything that you like. If you want to call this Charlie, you can call this one Charlie. If you want to call this James, you can call it James. But I think it's very important to use names that are understandable, that if you come back to your code at a later point, you're able to immediately see, oh, I want to do this. I've got this sort of pin. It has this name, so it probably has something to do with the screen. So in this case, it has a diode. So I can look at my component and I see, oh, it's also marked diode. It's from my standby frequency, so I know myself that's going to be that screen. And same goes for the CLK. Okay, here is CLK. I'm going to look at my component as CLK as well, so I can easily spot and correct my code at a later point if I would need to. And now we just go tm1637_6d. So what we're going to do is create a new screen. Now we're going to call it sec active freak, and it's going to be using the active, so it's going to be dio active, and it's going to use the CLK active. Here we go. So we create a new object of the tm1637_6d screen type, which is going to take pin 8 and pin 9. So here we say dio active, which represents pin 8, CLK active represents pin 9. Do this exactly the same for tm1637_6d sec stand by frequency. Now, same thing. It's important that they all have different names, so you can't have sec active frequency and some variables, and then once again create the sec active frequency. It can be done, but then it'll just override the other. So make sure that you use understandable names and also unique names. So we're going to be using dio standby and dio active. So now we've got all our components hooked up. No, that's not true. We still have a button. This is a bit redundant because we're going to put a remark button, but I just wanted to make some clear blocks for you that if I upload the code, you can easily see which does what. So we say const byte btn button is 7. And perhaps it's a good name because we also have our switch, which is the switch of the encoder itself. So const byte encoder button is 6. Now there is a chance that I mix these two up. Now because our encoder makes use of serial communication, we're going to be initializing the serial frequency or baud rate, sorry, 115200. Now you can change this to anything you like, 9600, but make sure that it corresponds with the connector. If you just want an out-of-the-box experience, sort of, don't change this, just go with 115200. and serial.set timeout 15. Now our screens need to be initialized and set as well. So we're going to be saying sec active freak dot init. And we're going to say sec active freak dot set, and we're going to say bright. Now it gets several options: brightest, bright darkest, bright typical. I'm just going with bright typical. It's just a matter of taste. Just see for yourself with the screens you have what works best for you, if it's a bit brighter or a bit dimmer. That's all there is. And we do exactly the same for sec standby frequency dot init and sec standby frequency I made a typo, didn't I? Yes, I did. Bright underscore typical. Text and yeah, here we go. Now there are some ways to shorten this code to make it more compact, but I'd rather have you see it blown up, expanded a bit, so you're able to see what is happening and more clearly see what is going on. And that's all there is to it, to the setup block. So we go to the loop block. We do connector dot data handling. Now what does connector dot data handling do? It listens to the serial ports it's connected to. If data is being sent, it will store the value that is being sent to the Arduino in the appropriate variable. So let's say you received a COM. Your computer is going to send COM to your Arduino. The moment it hits this part of the loop block, it's going to check, is there data coming in? If that's the case, see what data it is. It has all kind of logic in the background. Then store it somewhere, and then we can use it later on. So that is what's happening right here. Our screens are quite resource intensive. It takes quite some power off the Arduino to display the data and keep refreshing it constantly. And it's not really needed because a COM frequency only changes when we rotate a button or swap frequencies, etc. So it's not really necessary to have them refresh the data every time. So we're going to introduce some extra variables at the top. I'm just going to call it variables. So we're going to check that if the new frequency is different than the old frequency, only then we update the screen to save some performance and to make sure that everything runs more smoothly. So let's say our comms are still stored as a string. Yes, I know you're watching and you're judging me. You're right, I need to change this. String old com. Let's just do it like this. String. Oh. Let's do old active com, right? And now we do old standby com. So we also have a new one. So string new active com, string old, string new standby com. Here we go. So what we're going to do is new active com is connector dot get active com 1. Fingers crossed, but it was the right one apparently. So what this does is a variable lives inside its own block. Now what does this mean? Because we've put the old com and the new com outside of the setup and loop, this variable is going to remain. So we keep running the loop, going to update this variable, but it's not going to create a new variable. So it just creates a place for it to store the data, and the loop block just puts new data in or gets new data out but the variable stays the same. If we would do this, let's do new active com. If we would place it in the loop block, so new active com is connected.get active com, etc., it would run the loop block, create a variable new active com, assign the value, and then destroy it, create a variable again, assign the value, and destroy it. Now, it's not really necessary to use those resources, so I'm just going to put it up here. We don't want to recreate it every time, it's just there. Only the value is something that changes, right? So now we can do a check. If new active com is not equal to old com, old active com, only then we want to do sec active frequency dot display float. Now, why a float? A float is a decimal number. Pure coincidentally, the frequency 123.456 is also a decimal, kinda. So we're just going to use new active com dot to float, because it's stored as a text 123.456. It's going to convert it to a number 123.456 and then display that number. And that's basically just how the library works. Could have been otherwise if you did it manually yourself, but it's just the way it is. Now it's important that if the old com is not equal to the new com, that we set the old active com to the new active com. So we make sure that in the next loop, we're going to be checking against the new active com, the new old active com instead of the old one each time, because then it will be different every time something changes unless it goes back to the beginning. So we say new active com. Now do exactly the same for the new standby com is connector.get standby com1. Is this a thing? I'm not quite sure. We're going to see in a second. So we're going to say if new standby com is not equal to old standby com, sec standby frequency dot display float new standby com dot to float brackets end line old standby com is new standby com. Here we go. Now, what it does is the same as this block. Just make sure that you use the same of the proper names and don't use the same as you did up here. I mess this up all the time if I just copy paste and I forget to change a variable. So perhaps it's better to do it by hand, but just do what suits you best. And this is why it's also quite handy to use consistent and recognizable naming. Without looking at the top of my file, I knew that this is going to be sec standby frequency as the name of the screen, because the old one was sec active frequency. I knew that the new standby com would be called new standby com because we also used the new active com. So it really makes the logic in your head click more easily than having to go back. What was it? New standby com, that was, etc. You get the drift. This is all we need to display the data that comes from the game. The part that's left is the button and the switches and the encoders. So this library also has a very particular way of handling the encoders. It stores a kind of a value. Now, what does that exactly entail? Well, let's say it has the value 0. If you move up, it's going to become 1. It's going to become 2, 3, 4, 5, 6. If you move down, it's going to be 5, 4, 3, 2, 1, -1, -2, etc. So because we need to keep that in mind in our logic, we're going to be using another variable up here that's also going to be used as a check. So we say long old position is -999, because it's going to start at 0. So in the first iteration, it will always be different from the new position. And I will say long new position is, let's do it like this. So in the loop, we're going to be saying rotary inner dot read. Sorry. New position So because we also have an active and a standby frequency, we're going to be using old active position, new active position. Now we're going to copy and paste, but we have to make sure to swap out standby, of the active for standby. And because I'm using the 2.0 IDE beta, it's also already telling me that something is wrong because we have an active position and here we have a new active position as well. So it tells me you need to change the variable name. So that's exactly what we're going to do. Just change this to new standby position. So new active position is, I made a bit of a mistake because it's not the active position. Actually, it's, let's call this megahertz. This one as well. And we're going to call this, because we want to change the standby frequency, we don't want to change the active frequency. So that's why we're going to be using the megahertz and kilohertz. The inner one is going to be kilohertz, the outer one is going to be megahertz. So we're going to be saying new megahertz position is outer encoder.read. Is that how I called him? Rotary outer. Rotary outer. Dot read. Now it's going to return a number, let's say 1. The moment we click it up, it's going to be 2. The moment we click up, it's going to be 3. So this will just update this one each time. Now we implement some logic. If new megahertz position is not equal to old megahertz position, we're going to be doing something. What are we going to be doing? We're going to be checking if it goes up or down. So we say if new megahertz position is bigger than old megahertz position. And if that's not the case, so else, I'm going to do the other one. So if the new position is bigger than the old position, we went up. So we do serial.println connector dot. So it's going to be send com1 whole inc. Here we go. That's the one. Close the line. If we go the other way around, it's going to be serial.println. So if it's smaller, connector dot send com1 wall decrease DC. Here we go. So we already got the logic for the outer shaft, so it's going to be the megahertz. Now we just need to do a small minor thing, and that's just the same as with the standby comms, is that we set the old megahertz position to be the new megahertz position. So if it's different, make sure that the next loop we're going to be checking against the new old variable. Hope that makes some kind of sense. Now, because it's going to be a little bit tricky to just copy and paste with the naming, we're going to make sure that we use the new kilohertz position is rotary. We used to check the outer, but now we use the inner dot read. And we're going to be using the exact same logic. So if new kilohertz position is not equal to old kilohertz position, I'm going to be doing something. If it's bigger, the kilohertz position is bigger than old kilohertz position, we're going to be doing serial.println connector.send com1 fret inc. Once again, hope that this is the right one. I got the wrong brackets. Here we go. No. If that's not the case, so if it's not higher, it's got to be lower, right? So that's the only other option. Serial.println connector.send .1 fract decrease. And here we go. We need to set the old kilohertz position to be the new kilohertz position as well. So let's just do a quick verify to see if we made any mistakes, because we went through this quite quickly. We made a little typo. It send fract decrease, so DECR. It's a bit inconsistent with this one, so either one of those two needs to be changed. You're very right. Here I made a typo, rotary inner. Let's see. Here I made rotary with double I. And that's it. That's all the code that is needed. Let's just do a quick upload to see if this works. What I personally like to do is to do seg activefreq.display float 123.456 seg standby frequency. What this will do is, here we go, right? Yeah, what this will do is we'll just set the first variables to 123.456 so we can immediately spot if everything is wired correctly and everything is coded up correctly. So if we now hit upload, I selected the right board. We see that nothing happens with the screens, so we immediately know that something is up. I have a feeling that no, we're going to do it properly. Here we go. I have a feeling that it will take the CLK first and then the diode, so we mix these up. So let's see if that is actually the case. So I messed up the most basic step, and that's to check the pins. I had 8, 9, 10, and 11, but apparently I messed up and put them in 8, 11, and 9, and 10. So I could debug whatever I wanted. It took me an hour, but we are there. I even pulled out the oscilloscope from the closet. Well, it's not, it's just on my desk. Perhaps it will give you a small idea of what is happening. If we turn, here we can actually visually see the bytes being sent to the screen and the signals. So it just gives it a little bit more of clear sight of which pin is working and which isn't, which led to my confusion because both of them were working, but I couldn't see anything. So I was like, what is happening? But well, I was just stupid. It's 90% of the times that you think something's weird is going on, it's probably you, or in this case, me. So we got the connector. I'm just going to select my board, Arduino Uno in this case, going to hit start, and that should already be enough to get us going. Now, if I turn the inner knob, it's going to change the kilohertz, and if I turn the outer knob, it's going to change the megahertz. All fine, all dandy. There's one thing that we could add that we still haven't, and that's the button. It's quite a simple one. Pin mode, button, rotary button, what did we call it? Encoder button. Okay. Pin mode encoder button is an input underscore pull-up. Here we go. You could also wire up the other button as well, but I just want to give you a quick demonstration of what is possible. It's nothing really too fancy. You just go to the bottom of the loop. You say if digital read encoder button is equal to low. So that will tell us if it's low, the button is pressed, we're going to do something. What are we going to do? Serial.println connector.send swap FABCOM1. Let's see, is this the legit one? Expected before, oh, sorry, yeah. Mistake 1, so here we go. Since FABCOM1 is actually a command, so we're going to say delay 200. And delay is to make sure that in the time that we press the button, it's not going to trigger every microsecond it runs. It will just do it every 200 seconds. So if you do it a long press, a really long press, it will still send it every 5 times per second, but it gives us more than enough time to release the button. At least I hope. I always underestimate how fast that is. Now compilation completes. Going to I need to remove. Well, now it's a bit confused, so we're just gonna hit the restart button. I hope this will fix it. Upload complete. Okay, whatever. If you use a Uno, Nano, Mega, or any other one of those chips, we're going to need a capacitor. I've been using a 4.7 UF one. A 10 UF will work as well. You need it to make sure that the board doesn't reset every time it receives data of a serial. Now we're going to place it between ground and reset. And I'm not quite sure if you're able to tell, but it has these. It has a side that's black and it has a side that's white with dashes. The dashes are the ground side and the other one goes to the reset. Okay, so here we go. We have our reset, we have a ground. And we place it in. Now it's important that if you want to upload a new sketch, you remove the capacitor, upload your sketch and place it back in afterwards. So only if you use it for receiving data, you need it. If you just want to send data, it's actually not needed at all. So we're back focused on our radio stack. Open up the connector. I'm going to hit start. It's going to receive it. I see that it had a little bit of trouble with the standby frequency, but the moment we change the first one, it will automatically correct the other. Here we go. So that is working fine. Now let's see what happens if you 200 is a bit too slow perhaps, but we can see that it's actually quite simple to switch the frequencies, change it, switch it, change it. See, it's quite responsive. Sometimes it makes a little mistake, it corrects itself quite easily. I'm still working on the fixing, like smoothing it really out. It doesn't occur, but it's a work in progress. See, so that's working fine, and that's all we need to create our own radio stack. We just multiply it by whatever you want. If you want 4, you just do the same thing times 4. If you copy this code, make sure to, like if you want to add another section, make sure to change all the variable names to the new screens you're gonna implement. So if you add 2 more screens, make sure to give them a different name, make sure to give them different pins, and expand from there on out. You can also use other screens, other technologies. That's all up to you, but this is just a basic, well, I wouldn't call this a short tutorial, but it's a basic guide on how you can start creating your own. I've already shown you a little sneak peek of an extra feature that's going to be added besides the autopilot next update, but more on that later on. If you want to keep updated with more tutorials, more news and more updates, go hit the subscribe button if you haven't already. Hit the like if you like the content. Thanks to all my Patreon supporters for making these projects possible. It really keeps the train going. Thank you very much. If you're interested in supporting the channel, go check it out in the link as well. Once again, it's been a very long video, but I hope that I see you in the next one.